Hi everyone, this is Dr. J. Amarendra Rao, Principal VBIT Hyderabad. So in today's session, we will derive the general heat conduction equation in spherical coordinate system. Perhaps one of the most complex derivations in heat transfer, and also very important derivation as far as some competitive examinations are concerned. And in spherical coordinate system, the temperature would be a function of radial, vertical angular and horizontal angular coordinates as well as the time. Mathematically speaking, temperature would be a function of r, theta, phi and tau time. You may note that here theta is the angle measured in a vertical plane with respect to a horizontal plane, which means that this angle will be available in the front view. It represents the height of a point in a sphere, whereas phi is the angle measured in a horizontal plane with respect to a vertical plane. This angle would be available in the top view, and this angle represents the depth of the point. Analogy of theta and phi are latitude and longitude of a place on the surface of the earth. Latitude indicates the height with respect to the equator, and longitude indicates the depth with respect to the Greenwich meridian. So same concept we are going to have in this particular discussion. Then an equation which relates temperature with all the above variables is known as the general heat conduction equation. And obviously this equation would be a partial differential equation of higher order. And to derive this equation, we would be resorting to the first law of thermodynamics, Fourier law of heat conduction and the Taylor series. And to begin from the scratch, we consider an elemental volume in the spherical coordinate system having dimensions dr along r direction, r d theta along theta direction, and r sin theta d phi along phi direction as shown over here. And dr is the element dimension along r direction at any r as indicated over here. And theta can also be represented directly with the angle measured with respect to horizontal plane, and d theta is the angle, elemental angle at the angle theta. To represent phi, we consider the horizontal plane represented by the green line, and we are going to project it onto the horizontal plane to measure the phi with respect to vertical plane, and this angle is d phi. So this particular green ellipse indicates the circle which is perpendicular to the screen. And to make it more clear, we try to magnify this as shown over here. And we have the elemental volume represented over here. You can see that at any r we have dr, that's the dimension along r direction. At any theta, theta can be measured with respect to vertical in the vertical plane, or with respect to horizontal, that is going to be 90 minus theta, and d theta is the angle measured at some theta. Then you have r d theta is the arc length along theta direction as shown over here. So as far as dr and r d theta are concerned, there may not be many issues. But to find phi or to represent phi, we try to project this particular point onto the horizontal plane, we get an angle of phi. So phi is the angle measured in this horizontal plane with respect to the vertical plane. So we are going away from the plane. And at this phi, we pick up some element d phi. And to get the arc length, we try to project this r onto the horizontal plane. Since this angle is theta, this vertical component will be r cos theta and this horizontal component will be r sin theta. So this radial line will get reduced to r sin theta. And this r sin theta multiplied by d phi will give you this phi dimension of the element r sin theta d phi, which is the dimension which is normal to the screen. Therefore, we need to always consider r sin theta d phi in the horizontal plane as shown over here. As a result, the volume of the element in the spherical coordinate system will be r dimension dr times theta dimension r d theta times phi dimension r sin theta d phi. So once you understand how this volume is obtained, once we understand how this element is picked up, it becomes easy for us to derive the equation. Then we have various energies involved over here. Del QR is the rate of heat conducted into the element along r direction, shown by pink color. And del QR plus dr is the rate of heat conducted away from the element along r direction. Then del Q theta is the rate of heat conducted into the element along theta direction. Del Q theta plus d theta is the rate of heat conducted away from the element along theta direction, shown by orange colors. This green color indicates the phi component. Del Q phi is the rate of heat conducted into the element along phi direction. Then del Q phi plus d phi is the rate of heat conducted away from the element along phi direction. And to make the situation more generic, we have some internal heat generation at a rate of q dot watts per meter cube. So once we understand how the energies are created and how the energy is generated, it becomes easy to carry out the analysis. And for clarity, we do the analysis in these three directions separately. First along r direction. And we have to know that the area available for heat transfer along r direction is the product of remaining two components, two dimensions, that is r d theta times r sin theta d phi. Then temperature gradient available for heat transfer is del T by del R. And using these two, if you write for del QR using Fourier law, we are going to get del QR as minus KR r d theta r sin theta d phi del T by del R, where Kr represents thermal conductivity of the element along r direction. And del QR plus dr can be expanded into Taylor series as del QR plus del by del R del QR dr. Now we assume that del QR comma S is the energy stored in the element due to heat conduction along r direction in a time period of d tau. Then obviously del QR comma S should be del QR minus del QR plus dr times d tau. Now first we substitute for del QR plus dr using Taylor series, then we simplify it to get del QR comma S as minus del by del R del QR dr d tau. Then for del QR we substitute the Fourier law to have del QR comma S represented by this complex equation, and this minus becomes plus. Then the terms which are dependent on radius should be retained inside, others should go out. As a result, r into r square will be inside, kr will be inside, then rest of the terms will be going out. Some or the other, we must make sure that this term is equal to dv, and we realize that this r square is missing. And to make this equivalent to dv, we multiply and divide by r square. As a result, we are going to have 1 r here, 1 r over here, and in the denominator we are going to have 1 by r square. Therefore, del QR comma S finally is given by 1 by r square del by del r square kr del T by del R dv d tau. Similarly, we carry out the analysis along theta direction, and the area available for heat transfer is the product of remaining two dimensions, that is r sin theta d phi into dr, and temperature gradient available is del T by r del theta. And remember, the dimension along theta direction is r del theta, therefore the gradient becomes del T by r del theta. Then the Fourier law would be minus k theta into r sin theta d phi dr del T by r del theta. Then Taylor series can be expanded as del q theta plus del by r del theta del q theta r d theta, where k theta is thermal conductivity along theta direction. Then we assume that del q theta comma S is the energy stored in the element due to heat conduction along theta direction in the same time period of d tau. Then del q theta comma S would be energy coming in minus energy going out into time period. Then for del q theta comma theta plus d theta we substitute Taylor series, and we are going to get it simplified as del q theta comma s is minus 1 by r del by del theta del q theta r d theta d tau. Then for del q theta we substitute the Fourier law. Then you are going to have del q theta comma s given by this equation. Then the parameters which depend upon theta are taken inside, k theta, sin theta. Then this r will be 1 by r square. Then you are going to have outside dr r d theta, r d phi d tau. Somehow this should become dv. For this purpose we multiply and divide by sin theta. Therefore in the denominator we are going to have r square sin theta. Then here sin theta is coming over here. Therefore this will become dv. So del q theta comma s will be 1 by r square sin theta del by del theta k theta sin theta del t by del tau dv d tau. Then we go for this is d theta, right? Then we go for phi analysis along phi direction. Area available along phi direction is dr r d theta. Then temperature gradient available is del t by r sin theta del phi. So this is the dimension which is available along phi direction. Accordingly, gradient will be del t by r sin theta del phi, which has to be taken in the Fourier law as well as in the Taylor series, which we are going to realize. So del q phi will be minus k phi dr r d theta del t by r sin theta del phi. Then del q phi plus d phi would be del q phi plus del by r sin theta del phi del q phi r sin theta d phi. Then we introduce a term called del q phi comma s as the energy stored in the element due to heat conduction along phi direction in the same time period of d tau. Then del q phi comma s will be energy coming in minus energy leaving into time period. Then as usual we substitute for del q phi plus d phi and we simplify it to get it as del q phi comma s is minus 1 by r sin theta del by del phi del q phi r sin theta d phi d tau. Then for del q phi we substitute the Fourier law, and when we simplify it we are going to have del q phi comma s as 1 by r square sin square theta del by del phi k phi del t by del phi dv d tau. And obviously this entire term is dv, therefore no need for any manipulation. Then we assume that del qs is the total energy stored in the element due to heat conduction in all the three directions r, theta, phi in the time period of d tau, which is obviously the combination of r conduction, theta conduction and s conduction. Then we substitute for del q r comma s, del q theta comma s, del q phi comma s, and we take dv and d tau common to get del qs as 1 by r square del by del r square kr del t by del r component plus 1 by r square sin square theta del by del theta k theta sin theta del t by del theta component. Then 1 by r square sin square theta del by del phi k phi del t by del phi component, and we have volume and time constant in all the cases. And it may be noted that Kr is thermal conductivity along r direction, K theta thermal conductivity along theta direction, K phi thermal conductivity along phi direction. Then we assume that del Qg is the total energy generated in the element in the time period of d tau, which is obviously rate of internal heat generation per unit volume into time. And this represents the total heat that is generated. And due to heat conduction and heat generation, the energy of the element will be increased by d in the same time period of d tau. Then using first law of thermodynamics, we can write d as mc del t by del tau times d tau, and m can be written as rho into dv, where rho is the density. Therefore this d becomes rho c del t by del tau times d tau. Then by making energy balance, we realize that total energy stored plus total energy generated is equal to increase in energy of the element. Then we substitute for energy stored plus energy generated in this energy balance equation. Then we cancel out the common terms, the dV and d tau, and we get equation 5 as 1 by r square del by del r square kr del t by del r plus 1 by r square sin theta del by del theta k theta sin theta del t by del theta plus 1 by r square sin square theta del by del phi k phi del t by del phi plus q dot is equal to rho c del t by del tau. So this is the most general heat conduction equation in the spherical coordinate system. So in many examinations you'll be asked to derive the general heat conduction equation in spherical coordinate system. Then you can follow this simple and streamlined procedure. And this equation can be simplified by introducing suitable assumptions. First and foremost, we assume that the sphere material is isotropic and homogeneous, which means that Kr is equal to K theta is equal to K phi is equal to K. Therefore, K can be taken common and throughout you can divide by K to get 1 by r square del by del r square del t by del r plus 1 by r square sin theta del by del theta sin theta del t by del theta plus 1 by r square sin square theta del square t by del phi square plus q dot by k is equal to 1 by alpha del t by del tau, where alpha represents the thermal diffusivity of the material. Then we assume that there is no heat generation. As a result, the fourth term on the left hand side gets lost. You are going to have 3 conductions is equal to unsteady term. This equation is known as the Fourier equation. Then we can assume that steady state heat transfer temperature is independent of time. Therefore, RHS vanishes, which means that R conduction plus theta conduction plus phi conduction plus heat generation should compensate for each other such that everything is in steady. This equation is known as the Poissons equation. Then we can have a blend of both steady state and no heat generation, resulting in first 3 terms is equal to 0. R conduction plus theta conduction plus phi conduction is equal to 0, and this equation is known as the Laplace equation. So like this, this particular equation can be subjected to variety of assumptions, resulting in the governing differential equation for those conditions. I may say 2D steady state, no heat generation. 2D steady state. First 2 terms is equal to 0. So 1 by r square gets out. Therefore del by del r square del t by del r plus 1 by sin theta del by del theta sin theta del t by del theta is equal to 0. It's as simple as that. I may say 1D unsteady, no heat generation. So first term would be equal to RHS. I may say 1D steady with uniform internal heat generation. Then first term plus fourth term is equal to 0. Like this, one can speculate variety of assumptions to make this equation simple and manageable. And perhaps the simplest is one-dimensional, steady state, and no heat generation. This temperature does not vary with theta, phi, and time, and absolutely no heat generation. Therefore, del t by del theta is 0, del t by del phi is 0, del t by del tau is 0, and q is equal to 0. As a result, temperature is a function of R alone. Whenever temperature is a function of R alone, no need for partial derivative. We can have first term is equal to 0. So 1 by R square will get lost. Therefore, you are going to have d by dr R square dt by dr is equal to 0. This is the governing differential equation for the temperature distribution in a sphere under 1D steady state conditions. And this equation can be integrated 2 times to get the expression for temperature distribution, and you can use Fourier law to get the expression for heat transfer rate. Now this is the general heat conduction equation in spherical coordinate system in the simplest possible form. Now let's try to look at some of the questions appeared in the previous papers as well as some general questions. And this was in 2004, GATE 2004. One-dimensional unsteady state heat transfer in a sphere with heat generation at the rate of Qg can be written as, and you can see that equation B should be correct. one-dimensional unsteady state uniform heat generation. So first term plus fourth term is equal to right hand side. Equation A looks to be good, but 1 by R, that's a problem. It must be R square. This is for cylinders, in fact. Equation C looks to be good, but absolutely no radius coming inside the parenthesis. And equation D is absolutely wrong because nothing is matching. Then one-dimensional unsteady state heat conduction equation in spherical coordinate system is represented by 1D unsteady state. So first term is equal to RHS. You can see equation A looks to be okay, but you are using D. When temperature is a function of R and time, you cannot use ordinary differential. Equation C is applicable for cylinders, right? And equation B looks to be alright. And equation D is wrong because you are using D by dr. Then 2D steady state heat conduction in spherical coordinate system is represented by, obviously you have to go for equation C, and this 1 by R square can be cancelled on both the sides or it can be retained, no issue at all. Then finally 1D steady state heat conduction in spherical coordinate system is represented by, many students go for option A, but it's del by del R. When temperature is a function of only R, no need for partial differential. So you have to go for option D. Option D looks to be alright. D by dr, R square dt by dr is equal to 0. Okay. So this equation should be alright. So equation C should be alright, not D. Not D. Equation C should be alright. D by dr, R square dt by dr is equal to 0. So this is for cylinders. This is for cylinders. These two are for spheres, out of which equation C is absolutely correct. So this is certain important aspects are related to spheres. So with this we conclude the session. So in the next session we will discuss certain more aspects of heat transfer. So with this, have a nice time.